cohesive energy equal to energy of free electron minus crystal energy. The amount of energy which is required to pull the crystal apart into the small pieces into a set of free electron or free atom is called the cohesive energy of the crystal. The magnitude of the cohesive energy vary for different solid from 1 to 10 electron volt per atom, except the inner gas, in which the cohesive energy is of order of 0.1 electron volt per atom. So we can see that the solid have much higher cohesive energy if compared with the inner gas. The cohesive energy control the melting temperature. So we can see from here. So you can see the cohesive energy here, 0.13 for sodium, 1.51 for magnesium, 3.39 for aluminium, 4.63 for silicon, and so on and so on. So from here, you can see the melting point for sodium is 371 Kelvin, magnesium 922, aluminium 933, silicon 1686, and so on and so on. So now, just now I told you that the cohesive energy is related to the melting point. Okay, so when I draw the trend, you can see that sodium to magnesium increase. Okay, actually I'm comparing from this row. Okay, from potassium to chromium, I think chromium, yeah, so increase and then decrease, increase to nickel, decrease to zinc, increase to germanium. Okay, maybe you can see the trend. Start from potassium, K, increase to V, 90, 178, 376, 468, 512, increase, and then 512 drop to 395, decrease, and drop to 283, decrease, and then increase again, decrease, increase, up to 372, and then decrease up to 11.2. So this is for the cohesive energy. When we look at the melting point, we found that it had the same trend with K, potassium, increase up to V, you see, same here, right? And then for chromium, decrease up to manganese, and then see the trend. So here we can conclude that the cohesive energy is closely related to the melting point. Therefore, when we know that when the cohesive energy possessed by the particular elements is higher, then the melting point is also higher. Okay, then this cohesive energy depends on the atom arrangement. Okay, so atom arrangement decide the cohesive energy and directly affect the melting point. Okay, so this is how we relate the atomic arrangement with the property of solid, because melting point is one of the property of the solid. Okay, so we have blue line and we also have red line. When I stack these two together, you can see that it's meshed quite well except for this small portion. Okay, so specific theory have to be explained for this part lah. Okay, so binding energy. A typical curve for the potential energy or we call this binding energy, representing the interaction between two atoms, is shown in the figure below. This one. Okay, so it has the minimum at some distance r equal to r. The potential energy is minimum when r equal to r naught, which is this point. Okay, for r larger than r naught, it means that the potential increase gradually, approaching zero here. This one is this line. As r goes to infinite. Whereas for r smaller than r naught, this region, the potential increase very rapid, and then tend to infinite at r equal to zero. Okay, so or you can look at this picture. So this is when r equal to r naught, when the u, the potential energy, is minimum. Okay, when r larger than r naught, this part, then the potential will increase gradually and approaching zero. The u will eventually go to zero when r is approaching infinite. However, for the other region, this region, r smaller than r naught, the potential increase rapidly. Okay, and then tending to infinity at r equal to zero. And the potential energy between 0 to the u naught, this is the energy needed to break the solid into small atom pieces, and we call this cohesive energy. Okay, so this is continue introduction to the binding energy. Since the system tends to have the lowest possible energy, because we know that the system always prefer to be in the stable state, and I also explained just now, when we say stable state, it means that it has the minimum energy, small energy, or smallest energy. When the system have high energy, that means that it is more active, unstable. Okay, so the system have the lowest possible energy, this point mu naught, this point when r equal to r naught. Okay, where r equal to r naught, this point, you have the minimum energy. Minimum energy means that it's the most stable state. So the corresponding energy u naught is the cohesive energy. So from sorry, what's wrong with this one? Okay, from here to here, this is u naught, and this is what we so-called the cohesive energy. A typical value of the equilibrium distance is of the order of few angstrom. Okay, so that the force under consideration are short range. Why is a few angstrom? Because the atomic scale